we go. I'm going to start off talking about Project 1, which we were gonna start this week, but I'm going to start next week instead, right? Should be a little more prepared for it. Project 1 has no sequential logic in it, is strictly combinational, right? So remembering the sequential means it has memories. Project 1 has no memory. It is just a simple combinational circuit. It is 2 pages, and that includes this little grading description of where your points are going to come from at the end. Make sure you read that, so when you submit it, I can give you points, right? One of the things that we're going to do, well, for Project 1, the main idea of it is we're going to build the main computational unit for a microprocessor, right? So I said the final project is we're going to build a microprocessor. This is the first bit in it, right? The first little piece. If we don't want to build the whole thing at once, that would be really difficult. The first part is called an ALU, or an arithmetic logic unit. It starts out looking a whole lot like a MUX, but has a little triangle indent in the middle like so. All an ALU is a block that can do multiple different mathematic operations depending on something that we will call opcode. If you were to go and pull up your project sheet, you would see that the opcodes that we're going to have are as follows. Okay. Add with a carry, exclusive OR, load, and hold. Your 2 input bits, you're going to have, bytes, B. 2 8-bit inputs that are going to come into this thing. Then you have an 8-bit result, which I'm just going to write R for results, which is 8, and a carry, which is 1 bit, okay? This is the block of what you were designing, right? I always like to describe it in terms of blocks, because now if you were to go ahead and write the top level module for this, right, you would instantly know that you would have 3 input ports, A, B, and an opcode, and 2 output ports, R and C, right? Those describe the entity. We're done. We know what the entity looks like. Now we just have to make it do what it's supposed to do. Real quick, how many bits does my opcode need?
15 down to 0.
No. So these are my operations that I can do. 3 bits, right? I need enough bits to put 1 opcode for each of these values, right? So anytime that you have to choose from a list of options, you need to assign enough bits that you can cover all of those. So if I tried to do this with 2 bits, 0, 0, 0, 1, 1, 0, 1, 1, I just ran out, right? I need a 3rd bit. Something like that, right? Doesn't have to be in order. You can choose. There's no real reason not to use that opcode list. In fact, it's kind of easier for me to grade if you use that order. But right, because if everyone's is the same, I know what to look for. That's all. And it also gets confusing because when I post like little screenshots that are helpful, I'm going to use that opcode ordering almost certainly. So that if you get lost, you can just go peek at whatever hints I have. I think I already even have some hints posted as you do this. So there's a bit of a reason that we're going to call this load and hold, which I'll get to, right? So add is obvious, right? It's just going to add. Add C is going to be A plus B plus A carry in. Okay, well, that means we need something like a C in somewhere. I don't remember where I put this when I ended up drawing it, but right, we're going to have some carry in. I think it goes on the A part, actually, doesn't it? Sorry, the A side. One bit. Yep. Okay. The Let's see what's those next. Great, yeah. So it's going to describe what these load and hold options do. If you go look at this table, which all it is load takes whatever value is sitting in B and puts it as the results. Hold takes whatever value is on A and puts it as the results. Now, the reason for that is going to be simply because the way we're going to implement this is it's going to have basically a feedback structure like so. Right, we're going to push it R back around. We're still going to have an output, but this way, if I want to hold on to a value, it can, just because I just keep A attached to R, right? May need an internal signal to do this, but you don't have to design this feedback signal just yet, okay? That one will, well, I think it'll come during this lab, but I don't remember really talking about it. Make sure that you're using these buses and name your ports at least something similar, right? So that we're all kind of on the same page. And then we're going to write a simple Vhdl test bench that it's going to give you this nice little table of, that it's going to give you what A's and B's and carry-ins are. And then you're going to test and see what the output is and see if it makes what it should be, right? So they're 1 byte, which is 8 bits, which is 2 hex characters. This gives you 2 hex characters to put into both A and B. And that's what you're going to turn in. I don't even think you need this one at all for this lab. Okay, or project, I guess I should say, because we're ultimately going to need some device that goes in between here and here that has some memory, so that we remember something to hold on to, right? Which we'll design for project 2, which is like not next week, but the week after, something like that. Yep. That should be all you really need. This is all we're going to build. Now, the one thing to keep in mind, this is why I believe that students get so confused with muxes, right? Is because this is a big block, right? It's going to be, and I'm going to redraw it. I'm not a very good artist. Okay, there we go. The big block, right? That has, again, ports A, port B, and I'm just going to use those for now with R. All you have to do is design modules that do each of these operations, right? So we're always going to conceive of what we need to do from the top level. What is our end goal? Then we're going to start designing either from the top down or bottom up. Either one of those is actually a fine thing to do. I prefer bottom up after I have the concept in mind, but I could do top down where I could, as I mentioned, all right, this is what I'm building. I could write the top level entity and then step down a level and try and build whatever is the next thing that I need to make this work, right? It's just like how when I talk about designing any VHDL, where I start programming, you go, oh, I need a signal, and then I go back and add the signal when I need it, right? This is fine. So let's say I went ahead, I write this top level entity in VHDL, and now I have an empty box. Now I need to look at, well, this is the goal. This is what I need to do, is do something with A and B, right? So in the case of add, I want to do the result of A plus B. In the case of this, it's A plus B plus Cn, right? That's the objective of each one of these. So let's go build one of those. You guys know how to make something that adds, right? Add. Now I go write an entity that is going to add for me. It's going to add 8 bits to 8 bits with a carry in, or sorry, without a carry in this case, right? So it's going to take A and B, and this right here is the add results. Then I'm going to jump down and say something like, I want to design the hold. Okay. Well, hold, I said, only cares about the A input, right? Hold is just take A and put it on R. So So if R, my output port, needs to decide between one of these two, based on an opcode, what do I use? A mux.
So your whole box is basically like just a wire, right?
This box?
Yeah.
Yeah, it's literally. Yeah. So in fact, this whole thing could go away, right? So what he pointed out, if you didn't hear because he's a little quiet, is that this hold is just a wire, right? It's just passing through the input. So I'm not doing anything to A, I'm holding on to A, right? So realistically, if I wanted to program this the laziest way possible, there is no hold option. It just plugs A into the mux then, right? And then if I send the command 100 to this mux, here's the opcode input, right? This opcode input just feeds over to the mux. I choose 100 as my mux select. It takes A and puts it on R. I've built an ALU. Right? This is the answer, right? You just have to go write the code, and the code is kind of dumb, right? You guys know how to build adders with and without carries. XOR is just a logical operation, right? That you can literally write export as long as you do it right, right? There's some syntax and issues in there. Load and holds, trivial, right? Easy project. 10 minutes tops, right? Yeah, no, I joke. But by the end of the 3610, at least when you take the following class, the digital systems, this is a 10-minute project. And most of that code is just the time it takes to type. In fact, if you type faster than me, it might not even take you 10 minutes. I don't expect you to be there, right? Obviously, this is kind of a learning process. What the main takeaways that I'm trying to get you to understand with this is this hierarchical design, right? There's a hierarchy to this. There's the top level, there's the submodule. We connect them together through ports and signals, right? This is really important concept, not just in digital design, right? We'll do the same kind of thing in analog and DSP blocks, all that kind of thing. This is a good introduction to how we think about larger scale systems. Build little blocks, stitch them together, you've made a thing. Make sure, I think the rating says something like, I can't remember. Read the thing carefully, like the whole lab, like the first time you read it line for line, highlight anything that tells you to do something, right? So if it says like include all test benches for each submodule, I don't know if it says that or not, but check and see if it does so that you get the points for that, right? The grading criteria are things that I like to point out that I'm going to judge you based on. This one is kind of qualitative rather than quantitative grading, right? I'm going to look at how you did it, make sure that you understand it, and that's where your points are going to come from. And do little comments on your code. You know how to do comments in VHDL yet? Right, there's an example right at the top of it. Everything starts commented out, so you can just scroll to the top of a new file and you see how to comment things. The comments that you guys will write should be designed to make it clear what the system is doing to someone that doesn't know what it is doing already, right? You should be handed to someone that is familiar with VHDL and have them know what it's doing. In fact, a good comment, you could probably hand it to any programmer, whether or not they're familiar with VHDL, and understand what it's doing. But that's what you should think about in your comments. Any questions on the project?
Is this what we'll do like for the next lab?
Yes, this will be next lab. Yep. And then the lab after that, if I remember right, is going to be a garage door opener, which is kind of fun. But we need today's lecture that I'm going to do now before we can do that one. So we're kind of weird. We're ahead on the labs. We're doing really well. You guys are doing very well this semester with the VHDL. So good job. But let's make sure we get this hierarchy thing down, because that's like the most important concept that I want you guys to walk away with out of this class, is how to connect blocks together. Because I hope to see all of you in my 3610 class in a year or two. And I hope you remember at least this much so that you can do well. Because that class is really fun, actually. It's hard, I'm not gonna lie. It's a very hard class, but it's very fun. technically, some of you will probably have what you need to take 3610 next year from now.
What are the prereqs?
This.
That's it.
I think it's this. I think that's the only prereq. And you have to be admitted to the major. The professional program is what we call it, right? Which sometimes we will waive, like if you're a student who is clearly going to make that GPA cutoff, there's a chance that you can get a waiver saying that you can start this now if there's like a spot in your schedule because you're done with all of your generals or whatever it happens to be. Because we don't want you to get hung up on it if your grades are really good anyways. That's the main point of the professional program, right? Is because you need a 2.5 GPA to graduate from this program. And we don't want you to go through 4 years and then not have a 2.5 GPA and fail to graduate because of a GPA. So do well in your classes. It's not that high, right? But we just make sure you guys are successful and get hired because it turns out employers don't like to hire people with lower than 2.5 GPAs. Okay, so last time, the main takeaway at the end of that is we have latches, which I'm going to denote with an L, right? This is going to be, in fact, I'm going to draw a D latch, and it's going to have a D input and a Q output, right? And it's going to have something like an enable probably, and then alternatively, we're going to have a D flip-flop, which also has a D, a Q. What does it have in place of the enable? The difference between a latch and a flip-flop. A clock, yes, thank you. What devices are inside of this conceptually, right? When I draw this, this is an abstraction. What is the next layer down? How did I build this? 2 latches, yes. I put 2 of these together in an intelligent configuration, and I end up with something that is clocked, right? There are several different kinds of flip-flops, right? There's the D. But we like the D flip-flop because it's the easiest, right? Because at a clock, it takes whatever is on D and puts it on Q, right? Similarly, I could also add like an enable and a reset signal to it, right? That's allowed so that I need a D flip-flop, so data on D, clock, and the enable to be true in order for that to put whatever's D on Q. The last thing is when we do this enable, right, there was a right way and a wrong way to make this clock enable, basically, is what we're going to call this. And the right way is that, right? Because then what happens here is when a clock hits, if enable is 0, then it just takes whatever is on Q, right? It just loops back around and takes it. That's why it works as enable. It's a very stable system. Whereas using an AND gate, which was our other option for a clock enable, right, was bad because it doesn't know the difference between a clock and a rising edge of enable on that AND gate. So you can clock in things that you didn't mean to if you do that way. Now, you've probably, if you've been listening really closely, you've probably heard me say this a couple different ways, right? I've been saying when a clock hits, right, or at the clock, or more specifically, the rising edge of a clock, right? This flag implies that it only cares on the rising edge of the clock. Remember from last time where I went through this kind of step-by-step of why the 2 latches together create a rising edge, right? Rising edge triggered device. If I wanted it to be falling edge, I can just put a bubble and that indicates that this is a falling edge triggered device. So when I say a clock hits, I really mean a rising edge of a clock, right? Or in this case, falling edge, right? Going from low to high, high to low. We also talked about like the timing of it, right? There are delays through these things. We need the data to be valid some amount of time before the clock hits and some amount of time after. That's your T setup and T hold, right? Your setup time, your hold time. Those are very important in making sure these work. Okay, we can, you imagine, right? So we've been talking about these buses, right? That have multiple values on. I can also go ahead and say something like, well, I want to have many of these, right? Or something that we call a register, okay? So when it's combinational, it's a bus. When we put that bus into many flip-flops, it becomes a register. I don't have to do anything special to this device other than indicate that inputs and outputs are buses. Do I need a bus for the clock? No, I don't, right? It's still one clock for all devices. Yeah. So it's 1 bit there, 8 bits in each. So same thing for the reset, right? Same thing for the enable if I have one. This is a register. It is a vocabulary word that we just use to imply we are remembering some number of bits using probably a D flip-flop. We can use other kinds of flip-flops, right? We have, actually, I don't even remember if we talked about them because I've talked about them in another class a whole bunch recently. These, S, Q. Oh, we apparently don't know any other kind of flip-flops yet, do we? That's okay. We'll stick to these for now. This is a register. Register usually implies D flip-flops. We're going to be using a D flip-flop register for project number 2. But they're really easy, right? So, let's see. Fortunately for us, right? So we talked about rising edge and how we use 2 latches, and you could imagine going and programming 2 latches, turning those into a flip-flop, using SR latches to build a flip-flop and then using those to create something edge triggered, right? Well, what we like to do instead is just write 1 line of code, right? We don't want to use multiple of a device when we can simply write this will let you know if there is a rising edge of a clock. That's all you have to write in Vhdl. It's super nice. However, this has to be in a process, right? So we kind of talked about process. Process is our first indication that it's going to be sequential logic. Now, I want to be clear again, if a process lists all of the inputs in its sensitivity list, then it is a combinational circuit if there's no rising edge. So we're starting to get more complicated ideas. Let me walk you through. So sensitivity list is a thing that goes in the process after a parentheses. We don't use that in the test benches where we first saw the processes, right? Because that process we just want to run all the time over and over and over again continually. And then we tell it to do this clock equals not clock. Actually, we haven't done that yet. Never mind. We'll do that in a moment. This is your sensitivity list. If I want it to be combinational, and I had like this circuit, right? A, B, C, D. If in the sensitivity list, I list A, B, C, D, all right, A, B, C, D here, those are my signals that I care about. In any one of those changes, it does this operation. It implements a combinational logic. Even though it's inside of a process, when the circuit simulates or synthesizes, which is where it turns it and takes it from code onto a piece of hardware, right, which we kind of started understanding this week, it will be combinational. However, as soon as I use a rising edge of a clock, or I don't have I'm missing any of the inputs on the sensitivity list, it is sequential. It's going to use flip-flops for you. You don't necessarily know how, but it's going to. It has to, okay? So in this case, I'm just going to go ahead and process on the clock, okay? So if the clock changes, it's going to have to evaluate if I want a rising edge. But this is not a conditional by itself, right? So let's extend that and say, normally I would tab this over more, but poor planning, if rising edge of clock. Then do something, right? This is now an edge triggered device, whatever I put inside of here. All right. Let's assume that I have an input port D and an output port Q, right? That's fairly reasonable to say I'm designing a flip-flop. Oh, ta-da! I built a flip-flop. Right? That's how easy this is. Clock changes, it decides if that was a rising edge. If it is a rising edge, let's put D into Q.
Could you switch D and Q and like have the arrow?
You cannot. And it is also important to note, thank you for asking that, you cannot ever put an output port on the right side of an assignment statement. That is not allowed. So if Q is defined as an output, I can't put it on the right side. Okay, keep that in mind. Yes.
Does that mean if you're writing that code and you write it incorrectly, will throw an error? Or it won't tell you?
It will probably throw an error. It's pretty good about that particular error. Okay, and it's usually pretty clear because, right, so the other one that I want to hammer home that for some reason my junior students are struggling with this year is if you have an error, go look at the TCL console, right, which is in the bottom on the left side of that menu. And then it's going to usually have like 3 red errors or 2 red errors and have descriptions. What you want to do is scroll up a little bit until you get to the point where there is a black error. And then find the first of those. And I don't mean like the first in the whole TCL console, because this TCL console could go like way up. I just mean there's going to be red errors, some other junk, then black errors, then other junk. It's that grouping of errors, which is going to be should be the same number of black errors as there are red errors. Generally, the black ones just happen to be more descriptive and useful for human eyes. And then at the end of this error, it will say something like sorry, I have to use red even though it would be in black, adder.vhdl, and it's going to have the full file path right behind this, and then line 7.
I like how it gives you a link. That's so nice.
Yeah. So you just go look, say, oh, it was in my adder VHD on line number 7. I jump down to line number 7. Say line number 7 is this process. That really sucks because it could be anything inside of the process, or the line whatever comes right before process, right? That's what that indicates. That's how you debug your VHDL. This is a very important skill to have, because if you don't learn that, then you get stuck on waiting for me to come help you, which wastes your lab time. Whereas if you can start learning to hunt down your own errors based on the line number, you will go faster and be happier. Okay, we can make this more complicated. Let's say that I wanted an enable signal on this guy, okay? Ta-da, I built an enable.
Can you combine those statements like if and?
You can. I strongly recommend against doing this, the combination of rising edge. Rising edge, you should stand on your own.
Is that the same reason like when we used it, when you drew like the AND gate? We'll do the same thing there.
No, it's actually simpler than that. It's the simple issue is if you get an error and you have combined rising edge and something else, the error
They're both on the same line, so you don't know which.
and it gets very obscure. It is a very unclear error when you do that. Whereas if they're separated, it gives you better errors. That's really all it is. Yeah. Also holds for falling edge. And thank you for asking, because if I wanted a falling edge, I could literally just write falling _ edge. Done. If you go and look at code on the internet for examples, you may see this rising edge used, or you may see an alternative form, which would say if the way we would say this out loud, if clock tick event and clock equals 1, we say tick for apostrophes generally in engineering, just because apostrophe is a really long word, right? So clock tick event. This tick event is just accessing what's called an attribute. We're not going to go into these in this class. We go into that 3610, which just says the event just means, is clock changing and did it change to 1? Basically. This is the same thing as doing a rising edge. It's just longer and less easy to read. Okay, so just be aware, I don't use this, but you may see it around. And may see it if I borrow code from Dr. Brown and some of his labs and kind of things. So just be aware, that's all I'm doing. It's another version of rising edge.
So if we wanted to add a reset, is it still the same like if then statement?
I'm going to do an active low reset here, right? Because active low resets are pretty common. And I'm doing this wrong, by the way. I want you to know this before I finish. Okay. Adult resets. Okay. So if I reset, then I'm going to put a 0 on Q, right? That's usually what reset means. If it's an active high output, there's no bubble, active high, therefore reset means it goes to 0, it turns off, right? Does anyone see why this isn't quite right?
Forgot your semicolon.
Ignore syntax for the moment and focus on function. Programmers should get this.
If enable, it only works if enable is not.
Yes. If enable is
It's an else
one,
if statement, so
because
if it goes to the if statement, then you miss your reset every time,
exactly.
even if it's not.
Yeah, so I'll do it again what he said. If the enable is 1, it will never evaluate, right? This is an otherwise, because it goes first. Is enable 1? Yes, let's just do this and move on. So it will never evaluate this reset question. So we have to rethink about putting it in order of what is most important. So this is saying that the enable is more important than the reset. If I switch that order, the reset is more important. Now, this is actually a wonderful opportunity to introduce the idea of asynchronous resets, okay? So this would be a poorly designed synchronous reset, okay? Synchronous reset means you have to have a rising edge of a clock at the same time as the reset, right? Because this rising edge statement is going to happen for one instant in time. And then it's going to ask the question, are we resetting? So if we have a timing diagram, right? Remember this word, and I drew a bunch of timing diagrams. Timing diagrams are really, really important when we're talking about things with memory. This is my clock. My reset does this, so clock reset. Does it reset? No, no reset, right? Because it doesn't recognize that this happens because it is synchronous. It is synchronized to the clock, synchronous, okay? We can, however, redesign this really quickly in order to be an asynchronous reset. And I'm just going to draw the new process. Process on clock. If it is asynchronous reset, our first change is reset, because our process, we don't want to have to wait on our process to wait for a clock change. We want to change if reset changes, right? Then we say if reset is 0, active low, RE is rising edge. I'm going to shorthand that pretty much the rest of this class because it's a big long thing, right? Else if, right now, remember else doesn't have the E and the else if. Else if rising edge of the clock happens, Q equals T. So this process says that if clock or reset changes, let's evaluate the process. So if reset changes and it goes to, and it's 0, then we reset. Otherwise, if clock or reset changes and it's a rising edge of a clock, Q goes to D. Right? And this rising edge is really important because the process is just asking the question, did clock change? If I don't have this rising edge, it will change and evaluate on both the rising and the falling edge of the clock, which is not good design.
Also want to check if we enable.
Well, yeah, if I wanted to enable, I would need to do another embedded kind of if statement in this rising edge, but I'll keep it simple for now. Okay, I've made a flip-flop. Let's make a register. The 4-bit register. Right, I have to change the input ports, right, in the entity declaration to make Q and D be 4 bits. So like a standard logic vector of 3 down to 0, and then change this reset state and da-da, I've made a 4-bit register.
And that's the equivalent of having 4 of those flip-flops?
Yes. Yeah, I have put 4 flip-flops in parallel that take a 4-bit D input and put it on a 4-bit Q output. All right.
Do the FPGAs use flip-flops, like
Yes.
actual hardware flip-flops on the?
Well, they're designed using transistors. So you remember how I drew like an AND gate in transistors, right? So like it resists an AND, well, let's do it an AND, right? Because it's easier, where I have a pull down and a pull up network.
Isn't it just like a lookup table and like flip flop combined together? Like the little logic blocks inside?
Not necessarily. So this is the pull down network, right? Then there's a parallel pull up network. Sorry, this is really poorly drawn, but I built an AND gate or an AND gate, right? And then I stick 2 of those into the cross-coupled configuration that we talked about using transistors. Now I have an SR latch. I stick 2 of those together, and I reconfigure those to get a D latch. I stick 2 D latches together, and I get a D flip-flop, right? So it ends up being 4 times 2 times 2 times 2 transistors in order to make a flip-flop, whatever that ends up being, right? These transistors, old technology, like bad transistors, if you want to go out and make a chip that is really cheap, are 180 nanometers long. So that's big for modern day technology, 180 nanometers, right? Small technologies are down in the 10 nanometer range now. We can make those. The issue is once you get transistors that small, you have to start accounting for quantum tunneling effects of electrons, and things get a little dinky.
Casual problem.
Yeah.
Getting too small.
Yeah.
So he thinks they'll get.
So I've done IC design in my past. I've designed like neural amplifiers and stuff using integrated circuits. When you do it in 180 nanometer, the data sheet for how to do that is like, I don't know, 100 and something pages. When you do it at 18 nanometers, which is the smallest I've ever done anything with, that data sheet is about 1,200 pages long, and it is an utter nightmare to try and make them work at all. Anyways, okay, let's see, what comes next?
TSMC thinks they'll be down to 2 nanometers by 2024. 2 nanometers.
That's crazy. Yeah, I haven't seen
hitting. That's like they're gonna have like 2 more processes, and then they're gonna hit. That's gonna be it.
We can go ahead and now do some more interesting things with these flip-flops. I just want to make sure that I don't skip anything that's actually kind of important here, because I went out of order on this versus the book, because I like presenting it this way, right? Just showing you how easy it is to take one basic code and start modifying it to get what you want, right? And how easy it is to make these things. There is, you can imagine using a D flip-flop, feeding it back around with a mux to make the clock enable, right? I could pretty easily have you do that. The issue is, I should probably draw it. DQ clock feeds back around to the mux. And this mux then, right, says something, and I'm going to call this signal data, and this will just be n. And what I'll say is data gets assigned to n when en equals 1, else q. Right? Boom, made a mux, right? That easy. Remember this when else. This is how we like to make muxes. You can use many when this, when that, when this, else this kind of thing, right? You can kind of chain that together. You see the problem why this doesn't work. There's a rule that I stated like 5 minutes ago.
The output is
Yes, there's an output Q on the right side of an equation, right? Problem, it doesn't work. So up here, we're gonna have to create some signal, internal Q. I'm not gonna write it out, right? It's gonna be standard logic or standard logic vector, however big we need it to be. Then we can, right? Because this one else actually still works if n and q and data are all 8 bits or 32 bits, however many I want, right? I can change the number of bits as long as I'm consistent. So now I create an internal Q. I can put this internal Q on that assignment. Now it's a signal, not an output. And then I just have to make sure that outside of whatever process that I'm doing, right? So I'm going to have a process on clock. This, right? So I'm inserting this internal Q to a D instead of Q. So it's a signal that's getting put into D. So we're putting in this kind of in this temporary area. And then outside of the process, which we say end process, I'm missing an end if, I know. Then we say that's all we have to do. We decouple the output from the input, and all that's really doing is just adding a buffer, basically. So it's like taking that, where this signal is our output, and then this is a buffered internal signal, right? Internal signal meaning it's not assigned to any port. One other cool thing we can add to this is we can use an output enable, which I mentioned one time, right? Which is a buffer with an enable signal that has the option to turn it on or off. You are going to be using this in project number 3. This is an important concept. When I do this, I can then say when OE equals 1. So what that is doing is it's now adding output enable. an output enable buffer that turns it on or off. And I'm just going to continue on, else Z.
Is that on the same line?
Yes, it's all one same line, right? This is just another when else statement. It is combinational because it's outside of the process. This Z, what it does is it just disconnects, right? It's not driving anything. It is just kind of floating there. This becomes very helpful later in the not too distant future.
And since it like goes to hardware, the order doesn't matter, right? Because you have that queue, you get that internal queue assigned like technically before you have that statement above, right? Or does it
Yes,
have to?
so int Q is always going to have a value on it. Is that what you're asking?
Well, I'm asking because in that data statement up there, you're using int Q before it's assigned to Q, but that's
Oh, yeah,
fine
order doesn't matter.
because it's hardware. So like
Yes,
they'll all get put together at once.
exactly. Yep. All processes and all combinational logic run in
Like
parallel.
if you're writing that in code, it would
Yeah.
be pretty good.
Yes, yeah. That's why hardware and
Q
software
doesn't
are
exist.
different.
What is this?
Yeah, exactly. So in Q there, so this is going to be our clock enable, right? That's what this is doing. And this is our output enable. Now we have a clock enable and an output enable. Both are allowed. This is how we implement both. Now, generally speaking, and this is really cool, clocks. Where do clocks come from? We know what they do now, right? Or why we use them is it keeps things synchronized, it keeps them in time, and this is like the fundamental idea of all of our digital logic. Clocks come from, well, many different things, but one of the things they come from is a crystal oscillator, which basically means we apply a voltage to it, it oscillates, and we get a clock, okay? They're pretty cool. However, they have a very limited frequency over which they can work. So typically, if you go look at your basis board, it actually has an oscillator on it that feeds into the FPGA that I can point out to you, and that generates a clock for it. The clock that results from it is 100 megahertz, okay? But let's say that you want to run something slower than 100 megahertz, like a counter, right? So like on your basis board, if you've ever noticed when you plug it in, first those little LEDs count up. Obviously, they are not counting at 100 megahertz or you would never be able to see that, right? 100 million times a second is way too fast to see this count up process, okay? So we need this thing called a clock divider, which takes a clock and makes it slower. It turns out it's very easy to do this in multiples of 2, okay? So let's say I take a D flip-flop. Right, you've seen this clock 100 meg. I have it defined in your constraints file because you need it. Oh, not F, sorry. I don't know why I did that. Q. Remembering that because of the way we design things, we always have access to a Q bar as well, and not Q. And no extra cost. It costs me nothing to have that Q bar access. This is how I make a 50 megahertz clock out of 100 megahertz clock. Let's use a timing diagram, right? This timing diagram is how we figure out everything. Why? So clock and how do I want to do this? We'll consider the Q bar output and the Q output, right? Because the input D is Q bar. So this is D slash Q bar. So clock is ticking along, right? And let's assume the Q bar starts out at 0, okay? Now we've talked about how I like to go ahead and just identify the important points of something, right? In this case, rising edge is going to be my important point because I drew it as a rising edge clock. So Q. Q is 0, which is our data input, right? So if not Q. So if not Q is 0, by definition, Q is 1, right? They're inverted of each other. Now, the clock hits, and after a brief amount of time, right, there's this thing that we talked about last time, which is your clock to Q delay. Like so. Clock to Q delay, so the clock happens, and then the clock is going to update Q with whatever is on D, which is a 0. So it drops to 0, right? And it can't change it most until the next point of interest, right? Next rising edge, so I can just extend that over. Well, because Q bar is just the opposite of Q, it rises to 1, right? At the same time, right? There's no real delay between Q and Q bar. There'll be a little bit, but we can kind of ignore that for now. Then another interesting point happens, right? Another rising of an edge. So Q says, oh, there's a rising edge. Let's see what's on. Oh, there's a 1. Let's update to the 1. This one says, oh, you flipped. I'm going to flip. Ta-da. There we go. And it just repeats over and over again.
Why is it offset from the first clock rising edge?
This clock to Q delay.
Oh,
It
okay.
takes some amount of time to go through those NOR gates or NAND gates, however we built it. Takes a little bit of time to cycle through and then update.
Okay.
Right?
It's not perfect instantaneous.
Yeah. Basically, because we can also draw it as not a perfect edge, right? Because it's actually going to take some amount of time to rise. That's all. I just like to keep you guys in mind of the non-idealities, right? Because circuits aren't perfect. And it's actually harder to go back and break you the habit of thinking that they're perfect than it is to remind you that they're not perfect.
Are there always anti-natural capacitance, right? Because it has to build that
Yes.
charge.
Yeah, if you're taking 1270, you would understand that that rise time comes from the capacitance of the devices. Which is why smaller devices are good, right? When I was talking about the 180 nanometers, 10 nanometer, that's why we like 10 nanometers, is they're smaller. Smaller means lower capacitance. Right, because if you haven't taken 1270, capacitors are literally just made by you take a metal plate, another metal plate, put them in parallel with some dielectric. In fact, air is dielectric, so it doesn't matter, and that makes capacitance between those two. Ta-da. So the bigger something is, the more the capacitance, slower it goes. All right, doing okay. We now have a new kind of flip-flop to talk about, which is really cool because they can be used to make, well, this clock divider could also be called a counter, right? We want to count things all of the time. With one flip-flop, it's not really counting much, right? There's really just one bit that is essentially counting 0 or 1 clocks essentially overflowed, right? Because
So
it's
you
the
can
same
use the
problem.
clock as your first bit.
Yeah, basically, because if you, I was going to point this out later, but here is 0, 0, here is 1, 1, here's 0, 1, here's 1, 0. I have all the possible numbers, right? I have a 2-bit counter right there that just cycles over and over again, right? The order is a little bit wonky, right? So we could go find our first 0, 0. Happens here. This is 1, 1. This is 0, 1 if I'm going down, and this is going to be 1, 0. So there are all of my numbers. So it turns out we're counting a little odd, but all the digits are there. Okay. Well, let's talk about another useful handy flip-flop called the JK flip-flop.
Wait, is that weird because you're using Q not on Q?
Probably. You don't build counters this way. Typically, we're moving towards that direction of how we're actually going to build a counter because they're really cool. We have the JK flip-flop. It has a J and a K input, just like the D flip-flop has a D input, right? J, K, I'm going to throw the clock in the middle for fun. It's also going to have a Q. Now, the way that we write truth tables for flip-flops is a little bit different, which is to say we want to know what is our next Q, And we denote that by saying Qn plus 1, right? I did a little bit of this last time, and we introduced the idea of what is my next Q. And then I want to enumerate all of my inputs. Ta-da, JK. And now we ask, what does J and K do? Well, this is actually a more versatile device, which all it says is, if you put 0, 0, I want to hold on to Q. Okay? Keep the same. If I have 1, 1, flip it. Make it not Q. Then we're going to use K as a reset and J as a set.
Do we get a Q not for free out of the flip flop as well?
Okay, I'll do that too. There we go. This is a JK flip flop, right? It's just not just data. It doesn't just pass the data along. It can be set, reset, or toggled or held, right? This is a very versatile, very useful flip flop. Something that we can do with it though that is kind of cool is that I'm going to erase something real quick so I can do this the easy way. What happens if I tie J and K together, right? So J and K can never be different. Well then, this becomes a new kind of flip-flop that we call a T flip-flop. The T stands for toggle. Because if T is 0, we stay the same. We don't toggle. If T is 1, we toggle it, we change, become not Q, right? T flip-flop. I'm not going to have time, unfortunately. I strung to do this because we only have, whatever, 20 minutes left. So what I want you guys to do is go look at page, I don't know what page, I don't have page numbers, figure 12-34, because that will actually show you how you used NAND gates and a D flip-flop to build a JK flip-flop. Okay. I don't want to draw it because I'm going to have more important things to talk about in my limited amount of time. But I do want to make sure you guys go look at it because you guys can understand devices, right? You can go look at a diagram and understand what it's doing. And now let's just quickly write some code for a JK flip-flop, right? I've got a truth table. I can turn a truth table into code really easy, right? My point here is that it's going to be just as easy to turn, well, a little bit harder, but basically as easy to turn sequential logic into code as it was combination, right? Combinational logic should be getting pretty easy to write into code because you're used to just writing AND, XOR, or the when else. Here, we just happen to know that we need to start with a process, and because it's a flip-flop, we're going to start with a clock, right? Process on a clock. When the clock happens, we want to do something. Since it's a flip-flop, we know we're going to have to consider the rising edge of the clock. Then we want to just make a JK flip-flop, right? Which is as easy as if statements, okay? Right, because we're just asking what are our inputs, raise it as a question. And the first question is, if J equals 0 and K equals 0, right? So here's your question from earlier is I can combine questions using logical operator and, okay? If J and K are 0, then, well, what happens to J 0? We're going to want to write something like Q equals Q.
Would we make J, like this is kind of redundant, but if we make J and K like a vector, two-size vector, and then just do the 0, 0, 0, 1.
Yes. Yes, you can. Now the book's code here is a little bit wrong, and I'm not going to use it because it doesn't have this. And I'm going to use this word state. We'll talk more about that, but it doesn't have this condition. Okay. And that's bad. In all of your code, you should always have all conditions enumerated. This is true in hardware. Software doesn't care, right? But in hardware, if you leave something undefined, if I left out this if or didn't put an else, it interprets it as don't care. And most of the time that means it will stay doing what it was doing, but not all of the time. Okay? So it is a bit of a trap, and be careful. And sometimes they'll just throw an error and say, nah, this doesn't work. Okay? So the other problem is, right, this can't be an output, so I would need to do something like a q int signal like I did earlier and put the q int later, like q equals q int. So really, I would have to do q, and I'm just going to use I. It's assigned to qi, and then way down here, I'm going to have the when else stuff for the q that I talked about earlier, right?
Are they both I? Like,
They're both qi. Because, good question, because you cannot assign a signal inside of a process and outside of a process. So if I put q in here, I could not do the when else outside of the process. So let's just deal with qi. And then put the q is assigned to qi when blah, 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 right?
Because outside of the process, it's like static. It's once you define something outside of the process.
Yes, kind of, but at a more simple level, if I have a block and it has an output, and I have another block, and one of these is combinational, one of these is sequential, and they're both trying to drive Q, and this makes it a 1, that makes it a 0, this is called dual driven, and it fails, right? That's why. This is the real reason why. Is I need something in between those two in order to make it not both driving Q. And that's what, but it does, it tries to do that if I put it inside a process and outside. Else if, I'm just going to do the shorthand so I don't run out of time, 0, 1, right? Well, what happens if 0, 1 on the J and K? Qi gets assigned to 0. Else if 1, 0, Qi gets assigned to 1, right? And these are bits, blah, 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 so on and so forth. Right? These are if else. It's just what is the situation with my inputs when the rising edge of the clock happens. And then I can and will give you guys homework that asks things like, well, given a clock and Jake inputs to do this and K inputs to do this or something, draw my output. Right?
And the last one's Q. The last one would be 1, 1, and then Q internal is equal to not.
Yep, exactly. Yeah. Am I going too fast? Are we keeping up? Are we making sense? Okay, I got some thumbs up. That's makes me happy. So we're talking about T flip flops or how to draw T flip flops. I'm not even going to show you how to draw a T program T flip flop because it should be trivial if you can do the JK, right? It's just if T is something else, this, right? Now we could do, the reason I wanted to not do that is so that I have time to do the fun things with the T flip-flops. Because on first glance, you would look at a T flip-flop and go, why, right? It's kind of the dumbest of all of the flip-flops. It doesn't do very much, it just toggles. But it turns out I'm gonna make sure I did this right because it's kind of a complicated circuit. But let's go ahead and do it this way. CE is going to work as a clock enable, okay? And so let's go ahead and look at a timing diagram, right? This is going to be the most advanced timing diagram we've done yet, which is what makes it a good example. And we're always going to go ahead and or sequential logic, start with a clock. Okay, and then you kind of need to assume that it starts somewhere, right? So we're going to go ahead and we're going to look at the first output I'm calling Q0, the next one I'm calling Q1, and the next one Q2. I could do something, and it may be helpful to call this D1 and this D2, just so we have this intermediate signal so we can see what's happening. But let's just assume for the starters that clock enable is 1, so that the D2 does the same as whatever Q0 is, right? Q0. Okay, so I'm going to go ahead and say that Q0, which is this node, right, that I've marked by the output, is going to start at 0. Now the clock enable is turned on, so this is 1, right? And with toggle, if it's 1, all that means is at the rising edge of a clock, and all these clocks are going to be tied together, okay? All the same clock. Now Q0 is going to go ahead and respond to the rising edge of each of these clocks by simply toggling, right? Because that's what a T flip-flop does. It just toggles. And as I said, CE is 1. Well, in this case, D1 is the same as Q0, because I said clock enable is 1, so it's just going to pass through. And now T is always going to be toggling whatever Q is, okay? So make sure I go ahead and do this right. Clock reset, Q is D1. Like I wrote something down wrong here, but let me double check. Q1, rising edge of clock, is it has the same clock. Q0 is the input to this toggle. And then the output, which is what we want to look at next, is Q1. Okay. All right. Now Q1. Q1 is going to respond to the rising edge of the clock and toggle based on rising edge of clock and if toggle is true, right? Which toggle is true if and only if Q0 is. Okay.
But there's
Q0.
an AND gate, so.
But I'm saying clock enable is true.
It's always true.
It's always true. I'm just going to leave this one as always true so that we are always counting in Q0. Okay. Now Q1 comes along. There's a rising edge of a clock, and now this is why I like to draw these little offsets. Right. I've been doing this for a long time, and now we're going to see why. Okay. Because if I drew this at exactly the mark, you have to ask the question: is it or isn't it true? Right. Because if this dashed line went right through that line, we wouldn't know. So let's shift it in a realistic direction, right? There's going to be a delay. It's going to be small, but there is going to be a delay. And because this evaluation happens instantaneously, it's missed it, right? So it is not true here, but it is definitely true there. Okay. So this happened, the clock happens, it's an interesting event, but I guess we'll start at 0, it makes a little more sense. But it's not enabled, the toggle is not enabled, so nothing happens. I hit my next interesting event, and Q0, which is the toggle enabled, is enabled. So it drops. After a little bit of delay, of course. same thing happens. Not enabled is enabled. Not enabled. Ta-da. Oh, shoot, I treated this as though that was a 1, didn't I? Let me, sorry, confuse everybody for real quick. There we go. Now let's at Q2. Q2 cares what Q1 is, and it cares what D1 is, or Q0, right? Everyone see that? So it's the Q0 and Q1 is really what D2 is, which is the toggle enable. So I could write this as toggle. I'm going to toggle if Q0 and Q1 are both true. Well, I'm going to start at 0 again, right? We're going to start at 0, 0. It goes along here. This is true. Q1 is not true. Doesn't toggle. Goes along 0, 1. Doesn't toggle. Goes along. Oh, look, 1, 1. I have Q0 and Q1, which is my toggle condition. I can count. Well, let's go ahead and look at this as this first section is 0, 0, 0. Well, let's reverse it and go 0, 0, 0. This section is 0, 0, 1. This section is 0, 1, 0. This section 0, 1, 1. This section 1, 0, 0. What did I build? A counter. Right? With just T flip-flops. And I can string these together, repeating this structure, right? Because this first one's a little bit of a special case, because it uses the clock and enable immediately. But I can string these together an infinite number of times, and I have an infinitely large counter. Of course, I'm going to run out of space on my FPGA or whatever devices I'm using. That's a counter.
And this, it like almost relies on the imperfections of the delay.
Kind of. You can actually simulate it, and it just views it as this kind of like delta t is all that delay is, because I can write the words after something to help the simulation work better. But this will use a delta t minus 1 and be like, okay, so it's not changed yet. But yeah, you're right. It is very difficult for me to explain this if I haven't already explained the clock to Q delay, because it's very hard to tell what should happen. That's why I've done it, right? That's why we started with the clock to Q delay before we did the counter thing. There is an example that you should 100% go do on 12.4 that I've ran out of time on that kind of combines the idea of the setup hold times and clock to Q delay. It's very useful to read. And then I will pick up with like the last 2 pages of this. You should still be able to do most of the homework, but you may need to read the clock speed section if you're trying to finish all of the homework for this before I get to it. But I do want, yeah, that's fine. I'll go ahead and wrap up. Before I do we have any questions on this timing diagram? Because this is, if you're not following this timing diagram, you need to come to my office hours or send me an email or something, because if you start getting lost on these timing diagrams, the rest of this class is going to kick your butt, like real bad, okay? So I know some of you are afraid to ask questions. I'm very appreciative of those that aren't scared to ask questions, both in here and lab, because it helps me know what you guys know. But if you're one that doesn't like to speak up in class because I embarrass you when I answer or something, make sure you contact me so I can get this cleared so that you don't fail the next exam in the final, because this is hard and confusing for some people. Don't be embarrassed, but it's super important. All right, thank you guys.